Welcome, everyone. For today's prep, we're going to keep looking at trigonometric integrals, but now we're going to look at powers of secant and tangent. And we're not really going to break this up into different cases of, if secant is odd power, we do this, and if a tangent is an odd power, we do that, and if they're both even, what we're going to do, so it's a little bit different than sines and cosines. What we're going to do, our main strategy is going to be do a U substitution. And because we're looking at powers of secant and powers of tan, the choice for you, we're going to have two choices. We're either going to let u equal secant x, or we're going to let u equal tangent x. So that's kind of our idea here. We're going to try u equals secant, see if it works. If it does, great. If it doesn't, well, then we try the other one. And what we'll see with these powers of secant and tan is that sometimes one of these substitutions will work and the other one won't. Sometimes both of them will work, so sometimes we'll be fine. And unfortunately, sometimes neither of the substitutions will work, and we'll have to try something else. So let's kind of go through what each of these substitutions would look like. So let's suppose we let u equal secant x. Well, the derivative of secant is secant times tan. So if this is going to be our substitution, the idea for how this strategy is going to work is we're going to peel off from our integral one copy of secant and one copy of tan and kind of slide them next to our differential so that we get our differential to match up nicely. Now, if we try the other substitution, let u equal tangent, well, the derivative of tangent is secant squared. So if this substitution is going to work, we need to be able to kind of peel off two copies of secant and put them next to our dx. All right. So let's see how this is going to work. And once we kind of decide on the substitution, then we're going to have to kind of convert all of our remaining trig terms to either secant or tan. And we're going to use a trig identity to do that. So our trig identity is secant squared theta is equal to 1 plus tangent squared theta. So this is kind of like our sine squared plus cosine squared equal to 1. So one way to remember this is when I write t's, they kind of look like plus signs. So the plus sign and the t. So 1 plus tangent squared is secant squared. And we could reverse this and go the other way as well. So if we wanted to kind of change this around, we could instead solve for tangent. So equally good, we could say tangent squared is equal to secant squared theta minus 1. So subtract 1 from both sides. All right, so let's see how this strategy is going to work. So our strategy is basically try a substitution. If it works, great. If it doesn't, try the other one. All right, so let's start with example 1. We got some powers of tangent and secant here. So we have tangent of x raised to the power 6 times secant of x raised to the power 4. And again, we have those two possible choices for our substitution. Maybe u equals secant x will work. And if that's going to be our choice for u, then what's going to be our differential? Well, the derivative of secant x is secant x times tan x. All right, so let's try this one. See if it works. And we'll be able to see if it works. Well, let's get into it. So if this is going to be our substitution, well, what we want to do is we want to make this differential. We want to kind of fit it in. So we're going to peel off one copy of tangent from this stack of tangents, and we're going to peel off one copy of secant from this stack of secant functions. So let's rewrite our integral. So if we take one of the tangents off, we'll have 5 left. And if we have one of the secants left, we'll have 3 left there. And let's move them next to our differential. All right. So the idea with our strategy here is the stuff we peeled off and moved next to our differential, we're saving that. So we don't want to do anything with that. We're saving that for our differential for our substitution. And where we can tell whether or not this substitution is going to work is because we want to let u equal secant. So that means everything left in our integral, all these leftover terms, all these leftover trig terms here, we want to get them in terms of just secant. So we want to change to only secant x terms. So that means we got to get rid of this tangent raised to the power 5. Well, how are we going to do that? If we go back up, what's our trig identity? Well, we have this trig identity that tells us what tangent squareds are and how we can convert them into secant terms. So the idea is the secant cubed here is fine. That's already secant. So we don't have to do anything with that. It's just this tangent of x raised to the power 5. We're going to have to switch that over. And the idea is, because we're dealing with tangent squareds, we're just going to break this up into a whole bunch of tangent squareds, as many as we need to. So if we do that, we can break it up into one copy of tangent squared. We can break it up into another copy of tangent squared. And then we're going to have one tangent left over. And then we've got our secant cubed and our secant times tan x. All right. So if we look, again, this secant times tan, we're saving that. We don't want to do anything with that. Now this secant cubed is good. We could get that into that's already secant, so we don't have to do anything with that. This tangent squared, we could do something with that. So again, we could just use that trig identity. This tangent squared, good. We could do something with that. The issue is this tangent. So again, if we go back up, this trig identity only works on tangent squared terms. So it doesn't work on just individual tangent terms like this. So we get stuck. We're able to get almost everything here, but we're not able to get rid of that one tangent that's left. So this is an indication that this substitution isn't going to work out for us. So back to the drawing boards. So we're going to cross all that out. So let's try the other substitution. All right, so what was the other choice? Well, we got powers of tan and secant, so the other choice is let u equal tangent x. So if that's the case, well then derivative of tangent is secant squared. And so the idea in this case is going back to our original integral, we want to start by kind of making our differential match. So we want to peel off 2 copies of secant now and put them next to our differential. All right, so let's see what we get. So we've got our tangent x raised to the power 6, and I got this stack of 4 secant terms. I'm going to take 2 of them, move them next to the differential, so that'll leave me with just 2 copies of secant, and then the 2 that I peeled off and moved next to my differential. Okay, so again, when we do this, those ones we put next to it, we're saving those, so we don't want to touch them. So those are going to become part of our new differential if this technique works. And it's going to work. So let's see. All right, so that means all this stuff that's left over, we want to get these into what ultimately is going to become our u. So we want to get these all into tangents. So we want to get these only to tan x terms. So that means this tangent of x raised to the power 6, good. That one's good. That's good as is. We don't have to do anything there. The only thing we got to do is we got to change the secant squared. And we have a nice trig identity that allows us to deal with just secant squared. All right. So now we can use our trig identity. And we've got our tangent x raised to the power 6. And then if we use our trig identity, we get 1 plus tangent squared. And then we've got our secant squared dx. So if we look, all the stuff here, we were able to get into terms of tangent x, except for the one thing we were saving for our differential. So once we've accomplished this, we're ready to actually do the u substitution. So we're going to let u equal our tangent. So when we fill that in, well, what's going to happen? Well, if we're letting u equal tangent, then that tangent of x raised to the power 6, that'll be u raised to the power 6. And then we'll have 1 plus, and instead of tangent squared, we'll have u squared. And the secant squared dx at the end there, well, we've been saving it all along. And now we're able to replace that with our new differential du. So when we did our substitution here, we replaced each of those tangents with u, and we replaced that secant squared dx with our new differential du. And so now it's just regular u substitution. And we should multiply all this out, kind of like we've seen. So if we do the multiplication there, what are we going to get? Well, we'll get the integral of u to the power 6 plus u to the power 8 du. Get the antiderivative. So now we can just do some power rules. So we get 1 over 7 u to the power 7 plus 1 over 9 u to the power 9 plus c. And then finally, we convert back. So we end up with 1 over 7 tangent raised to the power 7 plus 1 over 9 tangent x raised to the power 9 plus our c term. All right, so when we're doing these powers of secant and tan, it's not as nice as our powers of sine and cosine. So it's not as kind of formulaic as if one of them's odd, you do this, and if both of them are even, you do that. So you can kind of think of it that way, but there are cases where you'll run into where you just got to try some different things and see what works. So rather than trying to break this down into a whole bunch of like cases and subcases, which you kind of have to do with secant and tan, instead we're going to think of it in terms of try these two u substitutions. See if it works. If the one that you try doesn't work, well then go on, try the other one. And what we'll see in class is, again, sometimes both of these don't work for an integral, in which case there's other things that we try, but you don't necessarily start with those. All right, so we'll see those in class. We'll see you then. Bye-bye.